All right, so our second talk this morning is by Semyon Dyatlov from MIT, who will speak on semiclassical measures for Laplacian functions in quantum mechanics.
Thank you, Joseph. Thank you so much to the organizer for inviting me to speak. It's a great honor to speak here in Chicago. And yeah, near the end of the talk, there will be a new-ish result. But I'll spend quite a bit of time on old results and also to give you a general overview of the question of semiclassical measures in quantum. So anyway, if we don't get to the new result, I think it's going to be fine. Let me just move the cursor away. There you go. All right. Well, the first thing I wanted to say is that, as many of you might know, very important person in the community, Steve Zeldich, has recently passed away. I wanted to dedicate this talk to his memories. It was something for the Northwestern University, just a bit north from here. And certainly a lot of results in quantum chaos, especially the particular part of quantum chaos that I'm going to focus on in the talk, are following his vision. So it's I think it's fair to say that I and a lot of the communities are still in shock that he left so right. Well, so there'll be more about Steve's math in a moment, but let me first state a result. It's a somewhat older result. It's all right, so here's the result that I can state on one slide. And then the setting is going to be a negatively curved surface. And so it's the result here is in the area of quantum chaos. Why do we study negatively curved surfaces? Well, one of the reasons is because the geodesic flow on a negatively curved manifold in general is a standard model of classical chaos. So if you perturb a geodesic slightly from its initial position and velocity, generically the perturbed geodesic will diverge exponentially fast from the original. So, exponential behavior, stable and unstable decomposition, which is something we certainly use. And then a classical thing to study in quantum chaos is Laplace eigenfunctions. So we have this manifold where the geodesic flow has a chaotic behavior, and then we study Laplace eigenfunctions on the same manifold. And so this is a quantum side of business. You can think of it in terms of quantum mechanics. If your universe was this negatively curved surface, then those eigenfunctions would be the pure quantum states of free particle. I'll normalize them in L2. So here's a theorem. It's a slightly old theorem, but you take any non-empty open subset of your surface, then the L2 norm of the eigenfunction on the subset is bounded below by some constant, which depends on the manifold, depends on the set, but doesn't depend on the eigenvalue. The lower bound on the mass. It's a fairly clean result to state. And you can think in terms of quantum mechanical interpretation that the probability of finding your quantum particle in any given macroscopic set is bounded below. So it's bounded away from zero as the energy goes through. That's it, if you want a physical way to interpret this result. So this is, this publication here. So the papers were written 3 years ago. The constant curvature case was done in joint work with Jin, relying on joint work with Zal, and the key ingredient coming from joint work with Bourgain. And the variable curvature case was done later in joint work with Jin and Nonnenmacher. All right, so these are the papers on that. Now, a rather different result, but in a curious way related to it. In the sense that it also is a result about lower bounds on Laplace eigenfunctions, is a result by Lagunov and Nonnenmacher, what I think they call it their Remez inequality, which is on any manifold. So you don't need a dimension assumption, you don't need curvature, just any compact manifold. You can get a lower bound, but in a way that depends on the frequency, so the square root of the eigenvalue. And you can see that if your set is not very big, then you get a bound that decays exponentially fast in the eigenvalue. What's novel about their result is that it applies to any positive measure set, and its lower bound only depends on the volume of it. It's a rather different result than what we do, because here we have a much stronger restriction than arbitrary non-empty open set, and our bound depends on it in some unspecified way. But what we do, which is something that these unique continuation type bounds cannot do, is that under our assumption, so negative first surface, we can get this bound for any fixed non-empty open set with a constant that does not degenerate in the high frequency. So our result is really interesting in the high frequency. Right? I should say, if you have to look at the paper of Malinnikov, and then this is not about the L2 bound, it's about L infinity bound. Now, I'm not an expert in unique continuation. My suspicion is that one can probably also prove something like that on L2 norm, but I don't. It's a slight line. What I see. All right. So coming back to our result. So unlike unique continuation type bounds, which are valid in any Riemannian manifold, we use strongly the chaotic nature of the geodesic flow. And here's a basic counterexample why we need this. Is imagine that your M was instead the round sphere, already came as a counterexample in the previous talk. Imagine that your omega is in your favorite, let's say the southern hemisphere, in the open southern hemisphere. Then you can see that the lower the mass of the eigenfunction omega can degenerate exponentially. There are Gaussian beam eigenfunctions that live on the equator, and they concentrate, exponentially. All right, I think that's it with this slide. Okay, well, here's a numerical illustration of what's happening. Here's on the left is a picture that's a dirichlet eigenfunction of the disk. So in the theorem, my manifold doesn't have boundary, but a disk is easier to plot, and here we should think about not the geodesic flow, but the billiard ball flow, and that's completely integrable. And so generic eigenfunction of Laplacian differential just looks like that. It's not too hard to plot. This is called Bessel function. Maybe that's how we originally appeared in that. And so you see you have this big white space in the middle. And in fact, it's again for a generic eigenfunction, it's exponentially small in this volume. So it's kind of a boundary analog of what happens in the sphere. Now, on the right is the hyperbolic surface. So this one is much harder to plot. So this picture is courtesy of Alex Strohmeyer. So hyperbolic surface is a constant negative curvature surface. You can always view those as quotients of the hyperbolic plane. And here I take a Poincaré ball model of the hyperbolic plane, and there's a fundamental limit. So you glue these pieces together, correctly get a fuse. And here's a plot. So here you can see that Alex's color coding is zero. I guess he doesn't care about zero that much, but his color coding zero is orange. So there's no orange space. I mean, there's plenty of orange space, but there's no macroscopic orange space, right? So of course the eigenfunction has zeros, and a lot of them. And in fact, no, I'm by far not the best person in this room to talk about zeros of that eigenfunction. So the microscopic features are also very interesting here. But if you think about the macroscopic feature, that you just take a fixed open set and then you count how much mass is there, well, at least it's always going to be bounded to the left. And in fact, more appears, it seems that it's really equidistributed. And that's a conjecture that I'm going to mention. Okay, great. So, well, now hopefully I won't lose all of you on the third slide, but so the way that I want to talk about the proofs, and I also want to talk about connections and general questions in quantum cases related to that. And in order to do this, I need to introduce a bit of microlocal terminology. So it turns out that in order to study eigenfunctions the way we study eigenfunctions, it's useful to not only localize eigenfunctions in position by restricting them to sets, but also localize them in frequency. And in fact, there is an asymptotic way of doing both. And so that's given to us by something called, here I take a semiclassical version, it's a semiclassical quantization, which is on Rn, you can think of taking a function of two n variables. The first n is the position variables, the second n are the momentum variables physically, or they will be cotangent vectors really. And then you can take this function and you can quantize it to obtain an operator. So formally, you can think of it as replacing momentum variables by this differentiation operator multiplied by h, where h is going to be a small parameter whose value I will address in a moment. Okay. Of course, this doesn't really make sense because those two operators don't commute. Multiplication, differentiation don't commute. So there is some work needed to make good enough sense of this procedure, and it has nice properties in the limit as h goes to 0. So some basic examples, a quantization of, well, any function of x will be just a multiplication operator. So if you don't depend on momentum variables, you just get a multiplication operator. And on Rn, if you quantize xij, you just get this differentiation operator. This quantization, because it comes from quantum mechanics, right? This is a vendor kind of classical to quantum observable language at quantum mechanics. All right. So we will put h equals lambda inverse. So lambda square was the eigenvalue, and our h will be lambda inverse. I'm not really going to justify technically here, but what happens is, if you go back to this picture, I mean, you can't really see, it's very small, but the eigenvalue is about 5,000. The square root of the eigenvalue, well, I don't know what's square root of 5,000, but let's say about 20. That's not right. 60 is the better, right? It's less than 100, I know that much. So maybe 70, but about 71, right? So now you can believe me or not, but the size of those microscopic oscillation features, you see it oscillates a lot, is about 1 over lambda. About 1 over lambda on the correct scale. And so in general, it turns out that eigenfunctions, they oscillate at scale about h, where h is 1 over lambda. So h is the effective wavelength at which we study your eigenfunction. And then if you look at it, we multiply differentiation by h here. So if you have a function that oscillates at wavelength h, every time you differentiate, you expect it to be multiplied by about h inverse. You expect each derivative to grow at h inverse times the original thing. And so that's why normalizing differentiation this way is a reasonable fact. So here are some basic properties of this quantization, which maybe will convince you that at least it's an interesting thing to study. So products of composition of operators corresponds to products of symbols with a lower order term. So this is called the limit is h equals to 0. Adjoints of operators correspond to complex conjugates of symbols. Bounded operators. I'm lying. I should say more things really to be correct. But let me skip this. If A is compactly supported, then all of the things I say is hard to. But boundedness of operators, roughly speaking, corresponds to boundedness of symbols. So boundedness of operators will help. And then one particular statement that we use a lot in our side of quantum chaos is something called Yegorov's theorem, which is it relates to objects. The quote-unquote quantum object for me will be the half-wave propagator. It's here. It's like the wave propagator, but it's half. The wave equation, it's really 2 by 2 meters. So it's a half-wave propagator. And the other object is the geodesic flow. So here you see, I forgot to say, but when we are in the manifold, my symbol A has to be on a cotangent bundle. That turns out to be the correct geometric object, which is going to live. And this homogeneous geodesic flow, well, the geodesic flow can be considered as a flow on the cotangent bundle. A homogeneous means it always moves at speed 1. So it has a singularity the zero section, but I can come to this with right? So, and what Yegorov's theorem does is that it tells you that if you take one of those quantized observables, one of those operators of h of a, and then you conjugate it by the halfway group for some time t, then you're going to get up to again an error. You're going to get the quantization of the pullback of the symbol by the geodesic flow. So it relates classical dynamics, pullback by geodesic flow, with quantum dynamics here in the form of the halfway. All right, so that's a nice result, and that's really only valid for bounded times. Well, you can push it a bit more, and in fact, what we do is we try to push it to its extreme. But if you let your time go to infinity too fast, as h goes to 0, then this breaks down, and we'll actually see it now. All right, so with all that technology introduced, what I can talk about a little bit at least is semiclassical measures. So now we study high frequency limits of eigenfunctions. So one of the ways to do this is to look at the potential limiting objects. But what are the limiting objects? So they should be macroscopic limiting objects, because we study again macroscopic properties. So properties where your set or your observable is fixed, and then your eigenvalue goes to infinity. So it's a reasonable thing to do. I'll use the board here. Oh, you have good chalk. Is this the Chicago chalk? Great. You can study something like this. You can try to study a sequence of eigenfunctions with eigenvalue going to infinity. And you can try to study the probability measure which is absolute value j squared divol g. Right? From a physical point of view, it's a very appealing object because just the probability distribution of finding, of the distribution of your party, right, of the position of your party. And then you can try to study weak limits of that. In the sense of weak limits in probability. So let's make this, right? Ideal. This is the definition of any A, right? To try to study those weak limits, and again, it's a macroscopic thing because I first fix my continuous function A, and then I let eigenvalue infinity. So I'm not going to pick up, for example, the geometry of the nodal set. All right. Well, it turns out that what's more fun to study in a way because it gives you more information, but also it has more interesting properties. Is what some people call microlocal lifts of those. So I don't like this name all that much because I think those are the objects that should have been studied initially. And those weak limits are pushed forwards. Which is the so-called semiclassical measure. So imagine I have a sequence of eigenfunctions. Now I'm going to take h to be 1 over lambda again, so it goes to 0. And then I say that this sequence converges weakly to the measure on the cotangent bundle if you have the following limiting statement, which is very similar to this weak convergence of probability measures, except instead of just integrating absolute value j squared with respect to some function of A, what I do is I can take an arbitrary function of t star m, so we'll come back and support it. Then I can quantize it with this specific h, again an operator, and then I pair it with uj and uj. This has a nice quantum mechanical interpretation. That's just the average value of the quantum, it's the average value of the classical observable A if uj is the wave function of your quantum party, right? If you took quantum mechanics, you might not recognize it because in quantum mechanics it would be this bracket notation, but it's literally this. And so we want this to converge to the integral of A with respect to some measure, and so this would be a measure of t star. Now, in general, such limit might or might not exist, but there is a compactness theorem, just like Hellig's theorem, I want to say, for probability measures. There's a compactness theorem that any sequence here of two bounded functions will have a subsequence which has a. So if you understand all possible limits like that, then you have some qualitative understanding of how eigenfunctions can concentrate in high frequency limit. And because you take those operators where you can localize in position frequency, you actually get a sense of the position frequency, which is more than just the position. Okay, so here are some basic properties of these objects. So I say use a semiclassical measure if it arises as one of the limits of some sequence. All right, so there are some basic properties. Use a probability measure that comes from the normalization of uj. It turns out to be always squared in the cosphere bundle, so just on unit length vectors. That has to do with how I chose h. That's because I chose h correctly to match the frequency of oscillations of that function. Now here's a property that the weak limit on the base is not going to see. This measure is invariant under the J as flow. So the geodesic flow here I restricted to the co-sphere bundle. And the geodesic flow is not a flow on the base manifold, right? If you start famously, if you start at some point and you want to know where you're going to end up, not only you need to know your initial point, but you also need to know your initial velocity. So that's why this measure on the a measure on the position velocity space or position momentum space has a chance of being invariant under the geodesic flow. For a measure on the base, it makes no sense. Okay. Somehow these so-called lifts actually reveal more structure because you get this relation to the geodesic flow immediately. But if you don't like that, you can take those measures and you can push them forward to m. So just integrate them against functions of absolutely. And that you can see because the corresponding operator will just multiplication by a, you are going to get a weak limit of this formula measures. So they in particular contain the small class. Now in quantum chaos, we are hoping that our limiting measure would be the Liouville measure, which is essentially the volume measure on S star with the right density. And if you have a sequence converging to the Liouville measure, we say that these eigenfunctions are distributed. And then the opposite situation that we sometimes try to exclude is the most concentrated measure. Well, it has to be flow invariant. So the most concentrated flow invariant measure would be a delta measurement flow invariant. And so that's something that would be the worst case scenario, because the general idea in this corner of quantum chaos is that if the behavior of geodesic flow is chaotic, then eigenfunctions should be spread out. And so their measures could not be too constant. Now, all right, so well, here I view all the results on relation, on making this idea precise. So the first one is quantum ergodicity. So that's maybe something that we will launch this part of quantum chaos at least. And it's it was announced by Sherman in '74, but I think the first proof, at least available in the US, was actually by Zelich in '87. That's one of his. I think it's fair to say it's one of the most famous works of Steve, and that's how it was done. One of the many ways in which Steve's work shaped the field. What does it say? This theorem, it says that if the geodesic flow is ergodic with respect to the Liouville measure, so this is on a general complex Riemannian manifold, could even have a boundary, then there is density one sequence of eigenfunctions which converges to the Liouville measure in this case. So what it says in simple terms, most eigenfunctions are distributed under a fairly weak assumption of ergodicity. In the chaotic world, this is probably the weakest chaotic assumption. All right. Well, that's a great theorem, but it only works for density one sequence of eigenfunctions. There is an essential reason why. So it's natural to ask, maybe if we make a stronger chaotic assumption, let's say negatively curved or more than somewhat weaker assumption that the geodesic flow is an also flow, then maybe the whole sequence of eigenfunctions converges. So the Liouville measure. So there's no exceptional sequence that it can distribute. That was first officially conjectured by Rudy and Sarnak in '94. Zelich told me that he didn't want to conjecture because he thought it was going to be true, so he was working on proving it, and that's why his quantum ergodicity paper is 3 times as long as it could have been. Well, the conjecture still stands, however, despite effort by a lot of people. But it says that all eigenfunctions that we distribute. One very notable piece of progress is Lindenstrauss managed to prove it in a particular class of hyperbolic surfaces, which are arithmetic hyperbolic surfaces, where you have a lot of extra symmetries called Hecke operators that you can use to get additional structural measures and exclude anything that's not difficult activity. All right. So this quantum mechanical ergodicity seems to be out of reach for anything that's not arithmetic for now. But what one can do is maybe one can be a bit less ambitious. Namely, we can study all possible semiclassical measures, but instead of showing that the only such measure is the Liouville measure, maybe we can try to show that we show some kind of restrictions on possible semiclassical measures that we get. And so the first result of this form was by Anand Tarman and Anand Tarman-Nonnenmacher, and it takes the form of entropy bounds. So they showed lower bounds on the measure theory or Kolmogorov-Sinai entropy of any semiclassical measure. In general, the result is a bit complicated to state, but for example, for hyperbolic D manifolds, so D-dimensional manifolds, they show that this entropy is at least D minus 1 over 2, which is right in the middle. So the delta measure on a closed geodesic has entropy 0. I'm not going to define this entropy. It doesn't appear again for us. But the closed geodesic measure has entropy 0. So that's excluded. In particular, you know that you cannot have a sequence of eigenfunctions which converges to just a single closed geodesic, or considers a single closed geodesic, or income. The Liouville measure in constant curvature has entropy D minus 1. So in some sense, they exclude half of all possible measures. But of course, it's a big infinite set. Right? So you can say eigenfunctions cannot be too concentrated in the sense that you have a positive. All right. Well, circling back to results that I contributed to. Here's this somewhat more recent result that we assume that you have a negatively curved surface. It's really part of the same papers. It's just that's the kind of theorem that we prove. We show that every semiclassical measure in the setting has full support. So if you only care about the support of the semiclassical measure, then there's only one possibility for negatively curved surfaces. So I can say eigenfunctions cannot be too concentrated, but in a different way than entropy bounds. Of course, the support doesn't determine what the measure does. So both this and the entropy bounds are quite far from quantum unique organicity, but in different ways. So they exclude none, no theorem implies the other. Right. So in particular, this implies theorem 1 that I advertised in the first slide, that it's just because if you have any, if you have any sequence of eigenfunctions, then you see that the weak limit of any sequence of these probability measures has to be fully supported, because it is the push forward of this mu which is fully supported. It's in a way a weaker statement. And this plus compactness, for example, would tell you that you have to have a lower bound than any limit. It's a bit of a funny reasoning, because what we actually show is a lower bound, and then we deduce this. But if you want, you can see this. Right. So I'm not going to describe the proof of that. In a moment, I'm going to go to a toy model, and then I'll talk about the proof in the toy model case, which is somewhat similar, but also a bit easier to present. But the key tool in this theorem that, say, compared to the previous works, is something called the fractal uncertainty principle, which was proved in joint work with Bourgain. And it states basically that if you have two sets which have fractal properties, I don't really want to get into that too much, but they have a lot of holes. So I say they're porous up to scale h, which means that any interval, so they're subsets of R, any interval of size at least h has a subinterval of some fixed relative size that is not contained in your set. It's a quantitative version of saying a set is nowhere dense up to the scale. So you have these two sets. Then you can see that you can show that no function can be localized too much in frequency space on one of those sets and in position on the other set. And more precisely, it comes in the form of Storm bound. If you know that if you have a function L2 and it's localized in this dilated sense on the first set in the Fourier space, then when you restrict it to the second set in the position, then you're only going to get, the mass of that is going to be bounded based upon the power patience. But it's really, it's a way of saying there's so many uncertainty principles, but every uncertainty principle in a way says that the function cannot be too localized in position in Fourier space. That's one of the ways that is useful for us. And it tells you that a function and its Fourier transform cannot be simultaneously localized too much on a fractal set. All right. Now, one thing that's suboptimal here is that the fractal uncertainty principle, this key tool, is only known of subsets of R. So it's not something that's known for subsets of already R2. It's false. That's one of the reasons. It's a simple counterexample. But then you try to exclude this count, for example, but nobody so far figured out how to make it work in a way that we can find useful in dimension. With two, even though there is some very nice progress by Hanschlag and more recently Cohen, who actually Cohen did it for any set in the class of arithmetic Cantor sets, which is really was a very nice theorem, but not one that currently extends to give something like that for higher dimensional manifolds. And so because of this theorem is restricted to purposes. So we don't know how to prove a result like that in dimensions 3 and higher. Right. So that's not very good. And so I think, yeah. So now I'm going to say goodbye to Laplace eigenfunctions. Now I'm going to talk about a related toy model in which we can say something more, and in particular, we can get a version of this theorem sometimes, which applies to higher dimensions, but still uses the one-dimensional part as well. Okay, and so the setting is quantum cat maps. So I'll spend a little bit of time introducing those, since it's a very particular toy model. Not so many people work with it. So everybody here probably heard what a Laplacian eigenfunction is. It's a symposium on Laplace eigenfunction. But cat maps are more rarely cited. So we can think of the wave group of the Laplacian as quantizing the geodesic flow. And one way to think, one way to phrase it is that you have Yegorov's theorem that I put on one of the previous slides, which relates a half-wave propagator and full penetrating geodesic flow. Now, what I want to do is I want to look at a toy model where instead of a geodesic flow, I look at a chaotic map, and perhaps the simplest chaotic quantizable map to study is hyperbolic toral automorphism, also known as cat map. So it's just a linear map on the torus. So I'm going to go to the torus. That's why I'm going to go to the torus. And my phase space, which previously was the cotangent bundle of a manifold. Sorry, I have to apologize, but I have to go get some more. Will you forgive me for that? You subtract this from it, but it's just I'm sick. I am COVID negative, but I can still be sick and COVID negative.
That's kind of something. And the dash, and then you play this map.
Oh yeah, we'll see. Well, we'll see something. Unfortunately, I didn't actually bring the picture of the cat. But yeah, so my base previous it was a potential bundle of a manifold in which you look at the geodesic flow. Now my phase space is going to be complex. It's going to be a torus, and to set up the result, it's going to be a torus of any even dimension. It has to be even because I'll think of it as a symplectic manifold with the usual symplectic structure. Now, what's it? So I'll think of the first, it's 2D dimensional torus. The first D variables are position for me, and the second D variables are momentum or frequency. Now, the corresponding Hilbert space, so the analog of L2 of M, the base manifold, here it's going to be just L2 on the grid. So D is equal to 1, this is just Cm, who's finite dimensional. And this M is a parameter which corresponds to the semiclassical parameter this way. So it's basically like 1 over h. So instead of a sequence where h goes to 0, we'll have a sequence of m's going to infinity. So you should think of it as matrices or operators of finite dimensional spaces of growing size. And as the size grows, that's where the semiclassical limit appears. So it's a bit different than the Laplace eigenfunction setup, because for Laplace eigenfunction, you do fix your manifold and it's a spectrum of a single operator. Here we have a family of operators. Okay. So, and then you can define semiclassical quantization, which I'm not going to bother doing because I didn't bother in RM, so I'm not going to bother here either. But you can believe me that if you take a smooth function, the torus, you can quantize it, and you can you get a family of matrices, you get a family of operators on each of those spaces. If you think of dimension 1, if you take any function on the torus T2, then you can convert it to an n by n matrix. for any n. And the rules are the following, basically. If your function is a function of x only, so function of the first coordinate only, you get a discretized multiplication operator. So you get this function, you sample it with 1 over n, z over n points, and then you look at the multiplication operator. If your function is a function of psi only, so only of the second variable, then it's going to be a Fourier multiplier. It's going to be a multiplier conjugated by the discrete Fourier transform. So it's those two statements are true, but then you can actually quantize functions of x and psi. So if you want to teach some students who don't know much Fourier analysis stuff, and you want to teach them some micro-local analysis, that's maybe the simplest model in which you can actually prove things, because soul matrix is not out there. All right. So, but let me move on to how to quantize linear symplectomorphism. So I'm going to fix the linear symplectomorphism on the torus. So what is that? Well, it's determined by a matrix. So it's an automorphism. So it's an automorphism or a torus as an abelian group. And and I want it to be symplectic. So this means that it's going to be determined by a 2D by 2D symplectic matrix. Okay? It turns out you can only quantize things with this. The Jézéquel is a Hamiltonian flow that preserves the symplectic function. So I say that a unitary operator, really a family of unitary operators on those spaces, is a quantization of this matrix if it satisfies exactly Gorov's theorem. So conjugation by this operator is intertwined with pullback by this matrix. So this matrix gives you a map on the torus, right? The usual way, because it's A maps R to D to R to D and Z to D to D to D, so it maps the quotient. That's how cat maps work, right? And so you have this exact relation actually without any error in this toy model. Now, there's a small, not caveat, but you actually get a family of spaces depending on the twist parameters. So if you were working in cat maps, you can catch me, and there are all these things in gray about how to choose this theta and so on, but I'm going to spare you that. Okay, so I'm just going to take, if n is even and theta is equal to 0, then I don't care it. And I might as well. All right. So the previous definition was quite indirect, right? It was in terms of an exact Gorov's theorem, and it's just and an object that I really didn't define. So here is actually, if you want to do some numerical experimentation, this is all you need to know to set up a computation of a cat map, because you can show that any symplectic matrix, any integer symplectic matrix, can be written as a product of matrices of the following form, and I can show you how to quantize each of them in a very explicit way. That might not give you, understanding what happens microlocally, but if you want to write it up on the computer, here are the formulas. So one kind of symplectic matrix is this: lower triangular with this block triangle. So you have this matrix B there, and it should be symmetric in order for A to be symplectic. So what do you get here? Well, you just get a multiplication operator by this factor e to the pi I over n, and then the quadratic form given by B. So that's fairly all right, fairly easy matrix. And if you know some microlocal analysis, this is what it would be in the microlocal world, in Rn world, because this corresponds to the shear canonical relation where your position stays, and then you add something to the frequency, and adding something to the frequency corresponds to multiplying by this kind of oscillating function. All right. The other kind is this diagonal matrix, which is it's a symplectic lift of an SL or GL really DZ matrix. So you can put a matrix in inverse transpose. So that's also symplectic. And the corresponding quantization is the pullback. So you have the underlying integer matrix E, and you just pull back by E inverse, and that can be defined. That preserves, multiplying by E inverse preserves this grid, which is Zn divided by Zd divided by n. So you get this pullback. And if you have the Fourier transform, well, if you have this matrix, so this is the third one that you have to include. then the corresponding plane is the discrete. So there it was actually pretty explicit how to write this down. Not that we actually use this in the proof, but that's. And there is a long history of that going back to physics works by Hanna and Berry, and then because it's a very neat appealing model where you can do a lot of explicit computations, and you can also do a lot of numerics, and you can test your various great ideas about quantum chaos in this model. We did not ever approach quantum organicity in this setting, so the analog of quantum organicity before. There is an analog of entropy bounds, and there is an analog of arithmetic quantum mechanics. So a lot of quantum results have analogs. So, all right. So now I can state the newish result, which is I'm going to take a sequence of normalized, little normalized eigenfunctions of my map. So I have a sequence nj, so basically the sizes of the matrices, or how do you say, the resolution of the parameterization, right? If you have we should really think of nj as a resolution, right? It's like I have a 1 inch by 1 inch square, and then if my nj is say 600, this means I have 600 dots per inch in my resolution. If you do printing, you know what I mean. So it's really resolution. How many dots you have per unit level when you discretize. So now we'll let our resolution go to infinity, which means our h, which is 1 over 2 pi n, will go to 0. And then we get this family of matrices. And then they're bigger and bigger, and then we take a family of eigenfunctions. And with some eigenvalues, right? Different matrices are not necessarily related to each other. And so I get this sequence of eigenfunctions, and I say it converges to a measure if the following statement holds, which is very similar to what we had for many functions. That if I take any smooth function torus, quantize it, I get this family of matrices that I pair to UK, then I'm going to converge to the integral. So you can talk about semiclassical measures. So here's a theorem, it's joined with Jézéquel, and the conclusion of the theorem is that any semiclassical measure is fully supported. So it's supported in the entire torus, which is the same as the conclusion we had before, and you can project it forward to show that, for example, these UJs would have lower bounds in mass in any, in any fixed region. But we need certain assumptions. Yeah? The one assumption, and the more serious assumption, is that I want my matrix, I want my symplectic matrix to have a simple eigenvalue, which is separated, so which is larger in absolute value than all others. So I guess I can say I want it to have a spectral gap. So I want to have a largest eigen. It will immediately be real because it's symplectic. And I mean, that's a serious assumption. And that's that will tell me that I have a certain amount of anisotropic behavior. So when I iterate my matrix, there is a single strongest direction which vectors grow the largest. And I will be using this very soon. Right? And then it's like if you think about the analogs for manifolds, higher dimensional hyperbolic manifold will never have this because they are all the eigenvalues will be the same. The expansion rate will be the same. Here, so I assume that. Certainly a lot of matrices like that exist. And the second assumption is that the characteristic polynomial matrix is reducible numeration. We'll see where that happens. So under these two assumptions, we can show that we still have this full support. Now, condition 2 is not too serious in the sense that if it fails, we can still say something, but just instead of saying for it's full, we can show that it contains a certain subtorus which we define in the paper. And in particular, there is a counterexample. So I think Semyon Dyatlov told me about this counterexample, and then he referred to a paper by Kelmer. And then I go to a paper by Kelmer, and then he refers to private communication by Nonnenmacher. Yeah. So I don't know who this counterexample is due to, but you could say it's elementary. Of course, everything is elementary once somebody else has done it. Or at least a lot of things are. But it's just this. If we look at a matrix, which is this. So it's this symplectic lift, this block diagonal matrix. then the corresponding operator is just a pullback. Right? Now I have my grid, so I have my pixels, and I have a pullback by an SL DZ transformation. Well, in particular, the delta function at 0, which is just a coordinate vector, is going to be invariant under that, right? And in general, it's cool because it's just a permutation. You can find what the eigenfunctions are. And so in particular, you have this delta function at 0 always, and in the limit, this will give you a measure which is just delta of x and then big psi. And that lives on the Lagrangian submanifold, and our theorem tells you that you would encounter something like that. And so in particular, it's not fully supported. So here in higher dimensions, this is an example of something that could go wrong in the sense of the measure like that. All right. So maybe I'll get to the proof of that theorem at some point. Maybe I won't. But let me tell you about the 2D case first, where this is really a perfect analog of the theorem I presented before. And so this is due to Schwartz. It uses the technology that was developed there. But so in 2D, you just need to assume that your matrix is hyperbolic because it has no eigenvalues in the unit circle. That implies both. For hyperbolic matrix, characteristic of 2 by 2 matrix, characteristic polynomial is always reduced. And then you show that so in 2D, you show that every semiclassical measure has force. So one of the reasons this theorem is interesting, and the setting of quantum maps is interesting, and maybe that's what I'll spend most of my time on now, is that quantum unique ergodicity is false in that setting. So we make all these grand claims that we want quantum unique ergodicity to be true. Schreiser mentioned, and this was mentioned yesterday, we want better bounds in the while law, we want better LP and L infinity bounds and eigenfunctions, we want Stricker test, the list can go on, right? But if our proofs only use classical quantum correspondence to microlocal technology, it is not clear why those hypothetical proofs of those great theorems wouldn't work for this very simple quantum Kaplan model, which satisfies all the usual properties. Quantization has all the usual properties. Product rule, adjoint rule, commutator rule. Pythagoras theorem holds. In fact, Pythagoras theorem is exact. And yet, a lot of those statements fail for a specific example of this map or specific values of it. So of course, it's a very particular counterexample, but if you're trying to push past it, you have to understand where does your proof would fail or for this, or what's so different about hyperbolic surfaces and these cat maps. And so here's how QE fails. So that's a paper that I think should be talked about more in the quantum case community. Maybe it's just because it's old, it's almost 20 years old, but for Nonnenmacher and ever, which is this. Assume you have let's make it 2D. So assume you have a 2D hyperbolic matrix. You have a cat map. Now you fix any periodic orbit you want, and any number up to a half, from 0 to half, then you can find a semiclassical measure which has this formula. So it's going to be, the extreme case is that it's half of the Liouville measure, which is nice, so half dx big psi, plus half of a measure on any periodic trajectory of your choosing. Which is, it has full support, right? It doesn't contradict theorem 4. Because once you get at least an epsilon of Liouville measure, of course you have full support. And it just barely satisfies the entropy bound. So it's like you want to show that the entropy, so you can show the entropy is at least a half. If you want to show in the correct normalization, if you want to show it's strictly bigger than a half, you already have this counterexample. But it's certainly not the Liouville measure unless I'll assume. And there is another counterexample for Walsh quantized Baker samples, but we know what's wrong with that one. That doesn't satisfy price construction. All right. So so QE isn't always true. And in fact, here's a picture. So I don't want to talk about what this picture is of, but it's easier when you plot an eigenfunction, then you know immediately what you're plotting, right? But that's just in the position. Now here I have a sequence of functions, or I have some function, which is just a function on the circle. Well, it's sampled, so it's really in Cn. It's just a vector in Cn. I didn't plot the initial vector. It's not going to tell you much. It's just going to ask. Now I want to plot it in a phase space, so I want to talk about its phase space concentration. And so I want to plot something that responds to this. So when I think of the map from A to this quantum average as sampling or sunny A at those discrete points with some weights, and those are my. So this is basically shows you how your eigenfunction concentrates in the position frequency space, and then there are certain few more tricks you have to do, but they're all legit from my total. But then we can appreciate the picture. So a typical eigenfunction on the left has a lot of features. These are not nodal sets. Don't get too excited. This is just has to do with oscillation of Wigner eigenfunction. You know, I can study that too, but this is it looks kind of similar, but it's really a different kind of thing. So a typical one would look like this. And so if you're sitting far away, then it looks like it's perfectly great, right? And that's equidistributed. That's what quantum mechanism does. A typical eigenfunction would look like that. And if a fascinating macroscopic set will be proportional to the power. On the right is an example for Nonnenmacher de Vera comes to something. You have to take particular values of that. So for example, for this A, this value 10 points. There's a simple number theory. And then you see if you're sitting close enough, you can see that okay, most of it looks great, but then there is this scar. And it doesn't look like it's a big deal, but actually it's the way this is plotted is I think it's correct. So the mass on the scar is the same as the mass everywhere else. So half of the mass. And so that's the thing that's happening. And we have to deal with that. Of course, from a point of view of full support theorem, it's fine. It still has full support. But in general, it's not. Oh God, I still have, how long should I speak?
5 minutes.
Okay. I see. This is so until 12:10 to this point. All right, good. Good for me. So let me tell you a little bit about the proof and how fractal sets it here. And then maybe I'll just show a few pictures and then we'll be done. So, well, how do we show that you have full support of a semiclassical measure? Okay, let's assume you don't. So what this means is that there is somewhere an empty open set which is not charged by the net. Now I'm going to start speaking in extremely vague terms. When you're actually working on this business, you have to be very careful because microlocalization is not perfect. You cannot localize to a set that's somehow too small because at some point you start violating the usual uncertainty principle and it gets really bad. Why your statements stop making sense. But I'll say that for now I just have a macroscopic set. So I have my the eigenfunction of the catnap. I do catnaps here. And there is this big, well, not so big, but fixed size ball where it's very small. The mass is very small. Now, what happens is, so here's a way to write it down, right? If you take some symbol living in this open set, I'm going to call this set a whole. The quantize applied to you, get something small. Now, what you can show, and this is something that, well, I think it already appears in Stern, and certainly appears in Zelnich's QE paper. So that's a very typical way to get a hand on, flowing bearings, is that instead of putting op n of p here, we can conjugate it by the map, by this quantum map. So in a manifold, you would conjugate by the wave. And because your eigenfunction is eigenfunction of this map, the norm is going to be the same. This is unitary, and this just pulls out a constant. And so you would see, effectively what you would see is that not only you're small in the whole, now Yegorov's theorem relates this conjugate to a different symbol whose support is moved according to the map. So if your function is small in this ball, it also has to be small in the propagation of this ball under the map for time 1. And you can do it for a somewhat long time. At some point, this breaks down. But you can do it up to logarithmic time with a very precise constant. Okay? And so what you can show is that, okay, so your eigenfunction is small in a lot of places. So where is it not small? Well, it essentially lives, or is micro-localized, whatever that means, in the set of trajectories which, when iterated by the map, do not go into the hole for a certain range of times, which is very carefully selected. And so I'll split this range into not being in the hole for forward time and backwards time, and I call this as gamma plus and gamma minus. So somehow my counterexample eigenfunction should live on those two sets. On the next slide, I'll show you those. Now, if we can show that no function can localize in both sets at once, then we get a contradiction, because my eigenfunction then, in operator terms, it's going to be equal to itself applied to, this operator applied to it and this other operator applied to it. And then it would be, the product of operators applied to it plus a small error. If the product of those operators is small in norm, then you see that there's just no math, because you have to have math somewhere. The total mass is 1. And if you know that all you have to be localized on one set and the other set, and if you multiply localization by both, you get something with small norm, then it just can't be. Okay, well, there is a major cheating here, which we modify using a blueprint going back to the original work on the All right, so here are these two sets, and that's a picture. So this is the closest I get to a cat. So this is my cat, and here's my home in white. And here are the sets where you're not in those. Okay, so here's time 1. You can see, there is this other ellipse. This is you were not in the whole, either forward or back. Then you do it again, and your ellipse gets thinner and longer, right? So I'm using hyperbolicity. Just like for geodesic flow, we use a stable and stable. And I keep going. And then at some point, the resolution of the screen will not be good enough, which is actually a perfect analogy, because, believe it or not, the reason those quantum cat map counterexample works for Nonnenmacher and Jézéquel has to do with the same thing, that if you take a usual cat map and you have it on a screen of very specific resolution, it's periodic at some point. At some point, the resolution of the screen is so small that those thin streaks, you can't really see them on this resolution. And then you think, well, it should become even more chaotic, but for certain values of parameters, it loops back to itself, which is very strange, but it does. And here you should think of this resolution as 1 over the 3. Actually, not so ridiculous. So here, I don't know what the resolution of this projector is, but probably at least 600 dpi, right? And so you see, on this resolution, we can still see it. And you see, you have these two sets now, and they look like they have structure, right? They're not just some randoms. You have structure. So one of them, so you have here stable and unstable directions, which would be the eigenspace of your matrix, eigenvalue bigger than 1 and less than 1. And you see that one of those sets is moved in an unstable direction and points in the stable direction, and the other set the opposite. And then what you can do in a quantum cat map case is you can cut and then you can rotate, and you can get localization, position, and frequency instead of localization on these two sets. And that's something that's ruled out by the fractal uncertainty. So that's somehow how you know that you cannot localize in both. Let me skip that. Now, in higher dimensions, many things can happen. But what saves us here is that I assumed this, so I'll very briefly talk about higher dimensions. I have this eigenvalue, which is bigger than all others. Let me even say that it's much bigger, like bigger than square or whatever, just to make numerology simpler. Then, if you think about your phase space, it splits into three directions for me. There is a strong unstable direction corresponding to the biggest eigenvalue. There's a strong stable direction corresponding to its inverse. For symplectic matrix, lambda and lambda inverse, both have the eigenvalue. And then there's everything else. I call it the central space. So it says the emesis would say it's a partially hyperbolic. I don't even care that it's hyperbolic on the center. Never made this. And so what would happen is that if you draw those sets, they have a certain kind of anisotropy behavior. And instead of going through this, which is all of course great, and I'll show you a picture. So here is an approximation of an isotropic picture where the eigenvalues of the matrix is the double eigen, almost a double eigen. And then you see that, and here it's a 4D thing. 4D things are hard to plot, right? So it's a, I have a 4x4 matrix, and then I iterate it. So I intersect it with the generic plane. You just have a bit of imagination. You see how those poles, if I look, those smaller poles that I get, they're about the same aspect ratio as the bigger ones, right? And so it's all mixed kind of in a way that's really two-dimensional, and it's impossible to split. You need a two-dimensional fractal uncertainty principle we see that you can have a function localizing in position for your space, something like that. In this case, when you have anisotropic behavior, so here I dialed it, I chose a matrix which has a big spectral gap. So the largest thing is way bigger than the next thing. You see those holes get thinner faster in one direction than others because you have this strong switching direction. And when you look at it, it looks like it's really on a certain scale. So you have to intercept, use almost orthogonality, there's work needed, but on a certain scale on which you can still use almost orthogonality and get non-intersecting support property of semiclassical quantization, it really looks like a product of a 1D porous set and an integral or a disk. And it's easier to see if I turn it. And so you really get two sets which, after enough work, they really look like product of 1D set and an interval. And for those two sets, you can apply the usual 1D uncertainty principle, right? Uncertainty principle, and then just reduce this one. And I think that's, yeah, thank you for your attention. Sorry for running.
Thank you very much. Questions, comments?
I have a couple of questions actually. So one is, which part of this do you know for Schrödinger, let's say, on R? I mean the lower bounds or something like this on.
You mean for Schrödinger operators with potentials?
Yes.
Okay, so the question is, can one choose something like that for Schrödinger operators with potentials? And
obviously interesting ones.
I mean, in principle, if you took that paper with Jin and Nonnenmacher, which does variable curvatures, which does variable curvature surfaces, and if you happen to have a Schrödinger operator where the flow, the corresponding Hamiltonian flow is anosymmetric, so it has to be smooth, it has to be big at infinity, so the spectrum is discrete, right? So it has to be within the framework within which we can microlocal analysis can study this spectrum, right? Because there's so many different Schrödinger operators, right? But then the method should apply. That being said, I don't know if there is a single example of such Schrödinger operator. So I know there are some examples of Schrödinger operators on the torus, I want to say, with their guiding geodesic flow. I don't know if there are any examples of Schrödinger operators.
No, I'm starting with a more like straightforward naive question. You are on a flat space, you are on a RAM, you have, you are my favorite potential, which are probably different, but okay. I mean, like, even if you take, the potential which is finite to start with, but then you put the limits properly so that you don't actually wash out
you put the boundary.
The information. And then, I mean, it's still a valid question, right? If there is an open set in which you have a lower bound.
Right. So
it doesn't really fit into the scheme of that.
As I said, if you had a situation in which the right assumptions for us would be satisfied, because of course there is also, for example, the work of Dima-Jakobsen, which shows that if you just project, if you take say toral eigenfunctions and you just project them, well, I don't know, physical space might be predating Jakobsen, but Dima-Jakobsen in his thesis, he characterized all semiclassical measures for the torus without any potential. It's a non-trivial thing because you can have multiplicity. You did it, and they all project to full measure sets, to full measure sets. If you only one on the base, but it's a different kind of result. If you want this particular result, it would apply under correct assumptions on strong chaotic behavior of the Hamiltonian flow. The question is,
there are interesting potentials with
are there any potentials with this property? And that I don't know. I just don't know. Are there any? Might still be an open problem if there are any potentials on, say, the torus even, where the flow is anosymmetric. There might be a topological obstruction. I don't know. I'm just I'm a fake dynamical systems person. So that's why before you're trying to adapt our method and prove a theorem like that, the first question I would ask is there
my question was the result is true, not only the
I don't know. It might be a theorem.
I mean, yeah, but the result should be true under different assumptions and potentials.
Right. Well,
I mean,
but we use that also properties, and we use the Bourgain.
Yeah, can I ask another question, which is probably idiotic actually. But I'm trying to. I'm just very not used to your normalizations.
Many people aren't. Neither was Steve. He didn't like the H hammer.
Yeah, I don't either. So the results about the full support of the measure, does it actually prevent from having increasingly strong scaring, which actually moves? Meaning that, you know, you have one eigenfunction which is sort of localized against one, you know, scar-like curve, and then, you know, the next one is localized along another one, and it gets stronger and stronger and stronger, but it's not the same scar, so you don't have a clean spot to test.
Our things are set up so that they don't move a priori. We can't move our things, right? So we usually fix a sequence, and then we want the limit to be the same for every A. You see, if your A wants to move, then there are two options, right? Either your A will converge to something, in which case you might as well test against the limiting option. Or if it won't, then I think Bourgain compactness tell you that it has to become more and more rapidly oscillated, basically. And so if you're testing against A's which become worse with frequency, then it's no longer a macroscopic question, it's a microscopic question. Well, it is a very interesting, I don't have the results in my mind, but there's been a lot of work on if you take a bowl, how tightly you can squeeze this bowl to make quantum ergodicity still work, and you can squeeze maybe by power of a log in best situations. But we don't even do this here. I mean,
Riviere, right?
yes, I think Riviere, but I think it wasn't actually Xiaohan. I just I know that there have been a few references, and I don't have loaded, so I don't want to say to omit somebody. But we do not do this here. So you can try to squeeze in some non-pointed way, but the thing is, our dependence on the lower bound on the open set is quite lousy. So if you try to squeeze the open set, that very soon you can. Because the current uncertainty principle gives you very not, you know, the constant there is there.
Yeah, so you prove the L2 bound of eigenfunction is falling below uniform by lambda. I'm wondering if that kind of U can be replaced by the sum of eigenfunctions. Like, for example,
well, depending on what sum, if you take
like sum of eigenfunctions lambda k and lambda k less into some big lambda.
What we do know is that it's enough. Thank you for asking. It's actually a very good question. So results apply to quasimodes of the following strength. So you need. I'm sorry, I'm gonna go semiclassical. Otherwise, I'm going to make a mistake. So it's enough to require this O little of h over log 1 over h, and it's known as sharp. If you put O large, if you were, I know that's not the question you asked perhaps, but if you have them all stacked together and you ask what's the strength of a quasimode, kind of how big of a spectral window you can still apply it to, that is sharp. So there are results by Brooks and Esperatus and Nonnenmacher that tells you that if you replace it by O large, then you can construct pathological eigenfunctions to finally.
Yeah, it's basically so you say that if lambda is some range.
Yeah,
they have such kind of.
And that's the precise range, and there is a reason because we propagate for logarithmic time.
All right, so thank you very much. Thank you.